answers. So I edited the sprint assessment for, hang on, let me go ahead and repeat that. Okay. You are, this is not a, you are all, I appreciate, I get questions from y'all every so often, but it is every so often, content questions. So some of the admin stuff, I'm only discovering as long as I make sure to kind of probe y'all during the guided lecture. So I have adjusted the sprint assessment for sprint challenge 2. This was the one from last week. So that if you are, like if you got any questions wrong on the sprint assessment, you can now see which of the questions you got wrong. I've just made that adjustment on the sprint assessment. So if you want to make a second attempt or third attempt, you're more than welcome to it. Remember that you do have to get an 80% on the sprint assessment in order to pass a particular sprint. So in other words, because you need to pass all 3 sprints with 100% on your sprint challenge and 80% on your sprint assessment, in order to pass each unit at Bloom Tech, you want to make sure you've got those scores. So I've just adjusted it so that you can now make a reattempt on the sprint assessment, and you can actually see the answers that you got wrong the first time around. If you have any questions about this, if you're feeling like, hey, I had some confusions about one answer, like an answer, or I didn't get an 80% in the sprint assessment in the last few times, feel free to reach out. Gideon, I think you have a question.
So it's just 100% on that multiple choice.
80% on the multiple choice. 100% on the sprint challenge on the notebook itself.
Okay, I thought so.
Yeah. Let me just.
I don't mean to pry on this again, but I just am on the sprint assessment and it still says answers are hidden. So I don't mean to take more time.
Okay. Let me double check this. Thought I clicked save. This is which sprint assessment? This is sprint. So this is, so I'm on sprint assessment 2. Shuffle answer, allow multiple attempts, keep score, allowed attempts. Let students see their quiz responses will be marked only after their last attempt. Only once after each. Okay, only after their last. I clicked on the wrong thing. Derp derp. Okay, so for sprint assessment 2, go ahead and give that a check, if you don't mind, Justin. In the meantime, I'm going to show you, if you don't know like what your score is currently on your sprint assessment or your sprint challenge, you can go over to your Canvas dashboard, and I'm just going to show you how you can look at your grades or see your grades for each individual module. So if you go over to your individual module, you've got your data wrangling. I'm going to go ahead and adjust this to student view. You'll see that this is your DS38 for data wrangling and storytelling 1. You can go up to the left sidebar and click on grades. And the grades will show you, again, I'm logged on as a test student. So my material is missing. So no, your sprint assessment, you need to get for an 80%, that's approximately 10 out of 12. And your sprint challenge, you'll see that it's listed as 5. So you want to make sure that you've got a score of 5 out of 5. Now, we have time next week, or we have the rest of this week and next week, the first 3 days, Monday, Tuesday, and Wednesday, to either meet one-on-one or address any questions throughout the as part of the challenges, as part of our review sessions itself. So if you have any questions about this that you'd like to go over, reach out. I'm happy to address a question even in class next week. So before I continue talking, any questions so far? Justin, can you confirm if you can see the answers now?
I don't, but it's fine. I don't know why. It just still is the correct answers are hidden, but we can deal with this afterwards.
Yeah.
Anyways.
Maybe it's a matter of it only shows you the answer after you've actually taken an assessment.
Yeah, that could be it.
So let's, if you don't mind, at the end of the lecture, let's chat.
No problem. Sounds good. Thank you.
And remind me if I forget. So today we're diving into linear algebra. Oh no, one quick admin thing. Remember, tomorrow is Thursday. that means that at 5 p.m. tomorrow, 5 p.m. Pacific Standard Time, the third and final sprint challenge for Unit 1 will open up. This will be available to you on Canvas, very much like the first two sprint challenges. You can start taking it tomorrow, work on it throughout all of Friday. You'll also have, of course, your last module or your last guided lecture of Unit 1. Congratulations on making it to the very last lecture of Unit 1 tomorrow. And you'll be able to take an attempt on those sprint challenges. Starting tomorrow, goes through Friday. You do not have to. So the interesting thing about your sprint challenge for sprint challenge 3 is because it is no longer the first 2 weeks. You can take a little bit more time with it before you actually complete a submission, but you do want to make sure, again, that all of your sprint challenges and sprint assessments are completed by Wednesday of next week. There's a little bit of a wiggle room in the deadlines, but I generally request, for the sake of everyone working behind the scenes, to go through any audits on grades or any corrections. Please make sure that all of your material is done and completed for Unit 1 on Wednesday, end of day. Any questions about that? Excuse me. Okay. Let's then do some linear algebra. All right. So here's the thing about what we're going to be talking a little bit about today. We're going to be using the same data set longboats. I promise this is the last day of this week where we're talking about longboats. I try to introduce something a little bit different, or a different data set starting tomorrow, just so that we can keep it a little bit more fun. But the reason I'm using longboats this last time is to just maintain some amount of familiarity with the features that we've been working on throughout the last 2 or 3 days. But what we are going to be doing is we're essentially going to be interpreting and looking at some of the built-in mathematics of the linear equation formula that we've been working with so far. Now, up until this point, we've been talking about the equation for linear regression model as a simple matter of b plus mx, or your intercept plus your slope and its values. But note that this is an equation that we would use simply to draw the line for a linear equation. The actual process for building a linear regression model, for where a model essentially attunes itself to the values that it's working with, is a little bit more complex and requires a little bit of more mathematical computation behind the scenes. Now, moving forward, as you dive into Unit 2 and you begin to learn about the different types of regression and classification models that you'll be working with, a big pattern you're going to be noticing from the kind of class structure is that the implementation of a specific model seems to be very, how should I put this, repetitive. And that's because a lot of the Python models, you're coming in at a good time where open sourced statisticians and programmers have essentially taken the time to build a lot of really intuitive. I want to say the word intuitive, but I wouldn't say that it's like intuitive unless you're like you've been coding or have gotten familiar with coding in Python. But once you essentially learn how to build a pipeline for a machine learning model, a big part of what your code looks like is you take your data set, you implement and import your data set into whatever environment you're choosing to work with. You clean the data, or essentially you transform your data into a format that allows it to be processed mathematically by the model you're going to be building. You essentially look for your missing values, you check to determine what features you might be the most interested in using. You try to determine what type of feature you might be interested in predicting. In other words, you determine what your target variable is going to be. And then the next few steps is Okay, well, now I think that the most appropriate model for this might be a logistic regression model or a KNN model, or perhaps even a decision tree to determine what type of model I might be interested in working with. So note that those three steps are like part of it's part of the buildup before you actually get into the actual model part. Once you get into the model part, you'll notice that it's as simple as implementing the scikit-learn model that I did yesterday, where you determine what model you want to learn, you import your model, you instantiate your model, much like we did with our OLS. We do model equals OLS, apply the features we want to use. You fit the models, you fit the values to the model. In other words, you take your XY values and fit it to your OLS model. And then you simply, once you fit your model, you have your model implemented. And then it's a matter of either studying the results of the model parameters or to determine its performance or the metrics behind the model's performance, or otherwise use the model to predict new values. So those 5 steps end up being very straightforward once you understand that you're essentially just implementing a pipeline for the different models you're working with. What I'm trying to say is a big part of how the day-to-day is going to go is, all right, here's the data set. Here's how we're going to clean it. Now here's the model. The model returns some results, or maybe here's a prediction. That part is going to be very much repetitive, simply because scikit-learn essentially creates pipelines for that process. However, the reason for why you might choose a specific model over another might be a little bit more varied. So for example, if you're trying to determine a KNN or essentially a KNN model, that model is based on measuring the Euclidean distances between the values and your particular prediction. And based off of the values and those distances, you might create a model that clusters based on those the distances between those values. There's a mathematical process behind that, there's a mathematical reason for you to choose that type of model. So a lot of how your class is going to be structured is going to be like, well, here's the math behind this model. Here's why you would use this type of mathematics to choose this type of model for this type of data set. And so once you have talked a little bit about what that math looks like, the model is simply implemented by, okay, instantiate, import, instantiate, fit, predict, and score. So with that kind of process being repetitive, with like kind of being part of the process, this is how we're going to focus on today. We've essentially kind of reversed the order where we implemented our model. And now we're simply going to look at some of the matrix multiplication required in order to understand why a linear regression model works the way it does. With that long spiel, any questions so far?
What was the before the fit predict score? That's kind of
so it's import. So let me go ahead and kind of just demonstrate that from so you import your model. So let's say that I'm working with sklearn. I'm going to need to remember that I'm working with a linear model, and I'm going to import my linear regression. So that's me importing. Instantiating is instantiate is my LR equals linear regression. Now note, this is the same as what we've done with our model, where our model is equal to OLS, and then it's your target to your independent, to your feature, and that value is fit. Note that this is actually a couple of different steps, or this is multiple steps kind of put together. But in this case, it's from stats models, formula, API, import, OLS. So note this is your import. This is your instantiate and fit. So if I instantiate it up here, my fit is to call my LR model fixed to the XY. And finally, you can visualize your results where you take your LR value and check your coefficients, or you predict, which is where you predict, and here it would be a new value. So in OLS, you're essentially taking or interpreting the results of your model, where OLS, it's either params, which is what we've done over the last few days, or OLS summary. So note, the entire process that, like these very long notebooks that we've been working on for the last few days can essentially be summarized in about 1, 2, 3, 4, 5 lines of code. With OLS, we're actually including more lines of code that we need. Obviously, this isn't going to work because we haven't actually fit any particular values to our X or Y or to the values in this particular text. But note, this process and alternatively, this process is going to be very much the same process you apply to all of your follow-up models. You'll have to take a difference. There's a few extra steps that you're going to be adding to this process. For example, come week 5 or 6, we start talking a little bit about how you can cross-validate your different sets of values to determine a far more accurate baseline for what your model may look like. You'll also start taking a look at how to train, test, split your different values into a value that you train your model versus a value that you test your model on. We'll talk a little bit about this tomorrow so that you are introduced to the concept before you start seeing them in full on week 5. But I just want to make sure that you're aware that this process is very much a big component of how all or most of the models that we implement using sklearn works. It's all very repetitive. It's just a matter of understanding the math behind the scenes. Okay. So as we've said, we've taken a chance of how to build a model or how to have Python build the models for us. Today, our class is going to be divided into 2 parts. For starters, we're going to do a very brief, very generalized introduction to linear algebra. Particularly, we're going to be talking about how vectors and matrices are applied in a linear space and how those sets of linear transformations affect our eventual linear equation for our linear regression model. This is a very generalized kind of introduction to linear algebra. I don't expect anyone to have to remember necessarily how this works, but conceptually, I do want you to be familiar with the terminology and some of the use case scenarios for some of the terms we're going to be using, something like, for example, vectors. Finally, the next half of the kind of lecture, in this case, we take this concept of our vectors and apply them or essentially demonstrate some of its mathematical application, particularly in terms to how to define cosine similarity between 2 different sets of texts. So first and foremost, let's go ahead and introduce what a vector is. What a vector or the structure of a vector is essentially a dimensional value that can be potentially identified as having a direction. And I'll explain more of that in a moment. You see the syntax for a vector every so often represented as your lowercase value, say in this case, a lowercase a with an arrow over it. And then it is identified as what would be this square bracket, the square bracket syntax with your values included as a two numerical value. This, because it has 2 numbers in the scenario, is a 2-dimensional vector. Now, we take a look at a 2-dimensional vector. a big component of how you identify or what a vector can be identified as is a value that would have a direction from a starting point or an origin. Typically, the origin is referred to as 0, 0 unless otherwise specified. But with this arrow that we've just created, we've got a vector that begins at origin 0, 0. And from this value for 3, we can identify that this is a value that moves. With your 3 is it moves on the x-axis 3 spaces, and on the right and essentially on the y-axis, it moves up 4 spaces. These values can be these values can be determined or can be converted based on any given space. Now note what happens. Part of the problem here is that I have a limit to my x limit and y limit set. So let's go ahead and adjust this for our visualization purposes. And you can now see your arrow, because we're looking at a -3, it's now pointing in the opposite direction. Fairly straightforward, right? This is very easy to represent and easy to visualize because this is, in this case, a 2-dimensional vector. We can measure both an x and an y value to our values in this vector. However, it gets a little bit tricky when you start thinking about 3 dimensions, because a 3-dimension then incorporates a z vector, where you would have your values as your x, y, and then you're going to have to pretend a little bit that I'm creating a cube value for a kind of this radical for this next square value. That is a terrible cube. My apologies. But in creating that 3rd dimension, we can begin to see the direction of that arrow existing within that space. It gets even trickier when you start thinking about 4th dimension, because at that point, we need to interpret that it's not just a z value, but a 4th dimension that becomes a lot more harder to visualize. You can imagine it as a plane if you so choose, but it is essentially a value that can move within or move outside of that 3-dimensional space. And then it gets even trickier, for example, if we start thinking about a 10-dimensional vector. Can we plot it? Not really. It becomes a lot, as far as a visualization, it becomes a little bit too sci-fi to actually start to visualize. However, the mathematics that are built into calculating a 2 or 3-dimensional vector are fairly straightforward and can be applied to that same 10-dimensional vector. Before I move forward, any questions about this so far? Okay. In order to understand what we're doing or why we're using or even talking about vectors as part of our understanding of linear algebra, it's helpful to understand a couple of different components. For one, vector length refers to the norm, or the size of a specific vector, where we take the multiple values in a vector itself, despite whatever dimension or despite whatever size of that dimension that value is, and calculate essentially the length or the norm of the vector. Represented with these pipe values, these 2 vertical lines, you can measure the length of a vector by simply taking the square root of the sum of the square values. So if you take your initial vector value or your initial value, square that up and sum up those values. In this case, we can take our value of 3 and 4. In this case, they've inverted the value in this case. You square your 4 and you square your 3, you get 16 plus 9, you get 25, you get the square root of 25 to get the value 5. So in other words, that vector of 3 and 4, the norm of that vector would be equal to 5. With a vector dot product, we do something a little bit different. Because with vector dot product, the rules of multiplication are a little bit different. It's not as straightforward as multiplying the values from one to the other. We're essentially applying a set of changes from one vector to another. So when we talk about multiplication within, or one type of multiplication within calculating one vector to another, we are actually referring to the value of applying the value of one vector to another. And that's calculated, or that is referred to as calculating the dot product of two vectors. So if you have vectors B and vector C, you have these values. You essentially take every individual value, in this case, along the index of those two values, and multiply those values to each other. And then the sum of those values will represent the element-wise multiplication process of those two vectors. Since we are here, let me quickly pause for a moment in regards to see if there are any questions about this. Your attendance code today is 6340. So on the Zoom chat, 6340. Okay. So this part's pretty straightforward. There's just some mathematics that happens behind the scene between two vectors. Why do I need to know this? You don't really need to know this. You just need to understand what's happening with vectors and what happens from a mathematical perspective. Because how you build a vector into a value, or how vectors get applied in the sense of computer science and the sense of the type of analytics that we're going to be processing, is that we use both vectors and matrices to calculate or to interpret the quantitative values of the features that we're working with. So a matrix is, if you remember, is essentially what's referred to as a rectangular grid of numbers, where we can think of the values and their arrangement as a row and column. The values can be either square in nature. In other words, you can have the same number of rows and the same number of columns, or you can also have both different sets of columns and values. However, the way we refer to the values is, or the size of a matrix, is by referring to them as their dimension. And you notice that we'll actually refer to the dimension of a specific matrix as a row by column basis. So for here, A is 3 by 3, but for B in this case, it's going to be a 2 by 3 matrix. And note, this is no different. You take your long bones data set, which I haven't defined yet. So let me just quickly run a cell below for a moment, bring this back, and take a look at the shape. You'll notice that our data frames and our NumPy arrays are typically arranged with this same philosophy in mind. And that's because both Pandas data frame and NumPy arrays or matrices are essentially intended to have this type of mathematical or matrix multiplication application processed on those different data types. This is part of the essence of the kind of programming that we're working with. So obviously the shape of these individual values are going to reflect those mathematical components. So if we wanted to model the relationship of nitrogen composition within term and time, it's important to remember the equation as we built it out earlier this week. We talked a lot about the slope plus the intercept values and the additional and the individual values of those of the objects in that data frame. Note, when we talk about the I of a specific equation, we're referring to the ith of the value. In other words, this is the iteratable value for each specific value within our nitrogen. So this will be the nitrogen amount for the first row, then it's going to be the nitrogen amount for the second row. And finally, we have this reducible error value. Now, interesting thing about this, there are two different types of errors that we talk about in linear regression models. There's your reducible and your irreducible error. In both components, our goal is to try to minimize the error for any given data set. The value we can control is, of course, the reducible error. And the reducible error is essentially part of, for every single component, for every single value, we're going to expect there to be some error. If we draw a line through that first point, we're going to assume our line actually hits that first point. So the error would be very minimal. But the second you introduce a second point, let me go ahead and actually draw this out as part of the process. So here's our grid, here's our value. Here's our first point. Let's say we have our linear regression, we have both our intercept and a slope that we can consider. When you iterate through that first value, your line is going to hit that individual point on the mark itself. So your error would actually be fairly minimal. But the second you introduce another value in your linear regression line, your line is going to need to try to meet the most minimum error between both sets of values. So when we're talking about what the reducible error is trying to do is we're trying to reduce the error between both sets of value in this, between those 2 points. We introduce a third point, we can expect the line to do the same thing for all 3 points. You'll see that it adjusts just minimally to reduce the error between all 3 points. Our ordinary least squared model, which is the model we've been working with up until this point, is essentially trying to determine the least error between all collected values within the model itself. So note, we are now introducing our equation, or how the equation gets built by the mathematical process that we're going to see. Questions so far? Pretty straightforward stuff, right? There's nothing too unusual. It's just kind of math behind the scenes. If we take a look at our data set and begin to take each individual values from our data frame, we're taking our equation. We've got our predicted values. We've got our target value for the amount of time that a body has been buried. We have our intercept, which we will now begin to calculate by having our individual first row value for nitrogen. And of course, the reducible error that we can calculate from building these values into the equation itself. So to think of this notation, if we take all of our X values and all of our Y values into a dimensional matrix that we call uppercase X and uppercase Y, note that your Y value becomes your matrix with all of the values included, with your X axis returned as part of your X values. Note a thing that gets fit or added to your X matrix here. You'll notice that a series of ones has been added to this X value. And the reason behind that is that the process behind matrix multiplication, or measuring the dot product of a matrix multiplication, where is that information? I think that information is a little bit further down, is that it actually requires there to be a multidimensional value between your, that in order for a matrix to exist, it needs to be considered as at least having a little bit of a width value to it, so that the equation itself, or your specific value for your y-axis, can calculate against your against the individual values in that X matrix. A big component to also consider is that we're using our slope and our intercept values, our B0 and our B1, and every single instance of the error being reduced from our linear regression as part of the matrix itself. So when you build this as a regression model in the matrix format, what's being calculated is the two-dimensional values against your vector for intercept and slope against your matrix values for your reducible error. Now pause there for just a moment. Okay. And then note, because a slight consideration as far as how matrix math works. From an addition perspective, you're actually using matrix addition on kind of a row by row basis. The sum of two matrices is simply the value along the object itself. When it comes to matrix multiplication, things get a little bit different, where you can multiply two different matrices based on the number of columns from, you can essentially take any two matrices and measure the number of columns to make sure that they have to be equal to the number of rows of your second matrix. And that is a big component of why we essentially start to add some dimensionality to our matrix itself. Any dimension essentially will tell you what the dimensions of that product matrix will look like. So because we're not actually doing classical multiplication on these values, it's not essentially on a row by row basis. When we calculate the dot product of a matrix multiplication, we're essentially treating this very similarly to how we would calculate the dot product of a vector. The only difference is that we are calculating the row to the column of the first value, followed by the row to the second column of your second matrix. And what this returns is going to be a resulting matrix at the very end of your calculation. The process behind this is not, it's okay to do by hand if you're so interested, but note that in a lot of ways, we're going to have Python is going to be doing the dirty work for us. So understanding the calculation is not quite necessary. Like understanding or remembering how to do the manual mathematics is not quite necessary, as long as you understand that the result of two different matrices is going to be a square matrix, typically, of the values that you're working with. So with our long bones example, if we have our X matrix multiplied by the unknown slope and the values, we can expect to calculate the sum of every single instance of our intercept values, because the intercept will be applied. Whoops. In this case, our intercept will be applied to your numerical value for 1. That's the second dimensional value, plus the slope value for 388. So as you can see, what happens with our equation is that this vector gets applied to every single instance of 1, and every single slope value gets applied to your second value. And that's how you end up with an equation or a matrix equation that looks like this at the end. Second, you incorporate your reducible error, as part of your equation. You have the full set of the value, and you can then solve for your intercept or the total intercept in a way that returns the minimum, like the most minimal residual from those values. Now, there's a little bit of calculus that we're not necessarily going to go into for how you go from these set of matrices into what's referred to as the standard equation for a linear equation. But what is helpful, what is helpful to know is that in calculating the slope and the intercept, what you're doing is essentially transforming a set of vectors and matrices into a structure that can then be essentially interpreted in to a non-mathematics audience. Before I go into this next section, a quick thing about matrix multiplication, vector math, and how we interpret this. This is where the field of mathematics kind of goes into three separate directions, like mathematics physics, and computer sciences essentially treat vectors and matrices for different purposes. Because our purposes are generally analytical or statistics, it's important that a big component of how we use these calculations is as a method that sort of draws the line between geometry and physics, or geometry and geometry and physics, and that we're trying to imagine these values on a space or as part of a space. So with that said, when you talk about the transformation of matrix value, or when you talk about the conversion of a matrix or a vector value, a big way that you talk about how to calculate or apply these specific concepts is by transforming the value itself. Okay. Understanding that this equation is simply a matter of taking your different matrices, calculating those individual values to interpret your end result to solve for B. Let's talk about some of the different components that we're seeing at the very top of each individual value. A transpose matrix is a value where the rows and the columns of the original are essentially transposed from one side to the other. And you can picture this by this alphabetical data set or alphabetical data frame as how the values have been taken, where the columns now become the rows. If you see this as a part of your data frame, let's note that if we have your long bones data set, there's your long bones data set. You can transpose the value. This is with a dot T property. And note that the data frame itself converts all of the column values as rows itself. And you can see how your values, your 177.1, are all essentially the same along the diagonal. So there's 177, 35, 36, all the way down. Now, this is typically represented. Let me just go ahead and use dot head to make this a little bit smaller, because it's going to jump all over the place. We've got our first 5 rows and our value transpose. This is generally represented as this uppercase T or this little hyphen at the end of your uppercase matrix value. This is usually referred to as well as as a prime value. Additionally, the other component or the other term that we want to be familiar with is the inverse of a value, where the inverse of a value is going to be referred to as the reciprocal of a matrix that we used to generate it. So if we think of a fraction of a value being the reciprocal of its whole value, the fraction or the inverse of a value acts as the reciprocal as your original matrix. So if you essentially calculate this value as your matrix value, the inverse is essentially referred to as 1 over AD minus BC as your value is built out. Now, the inverse of it, so it's 1 over AD minus BC to the dot product of B, negative C, and negative A, or like that, or that specific matrix. When you multiply those matrices by its inverse values, we essentially return what's going to be an identity matrix. And this lines up with the kind of correlation values that we've worked with previously, where you take for example, long bones dot. So if you look at core coef and take a look at long bones, you'll see that this is essentially a much longer identity matrix for all of the values we're working with. But if I wanted to only specify my values for, let's say we create this as a 2-dimensional value, or as a value with just a few matrices, you can see the identity matrix being returned as 1s, and there should be a bunch of 0s in there as well when you actually take a look at the core coefficient of those two values. So when you look at this identity matrix, you can essentially expect that your values will track to the will track in a way that you can then convert them into a component of your linear of your linear equation. This is not something that where all matrices are inverted or can be inverted. Some of these values do have to be square to begin with. And so making sure that we can consider some of these invertible matrix, we just need to make sure that we are working with square values where possible. So, quick question, and just to see if you can give me a heads up as far as how to answer this. Is it possible, understanding this, is it possible to calculate or to multiply vectors or find, excuse me, is it possible to find the dot product of two vectors of different sizes? Thumbs up or thumbs down? Close. So the trick is you actually need to be very aware that in order to calculate calculate two matrices, you want to make sure that your rows are the same size as your columns. So the trick then is that this is a big reason why when you work with, when you're trying to create an equation with missing or null values, your linear equation or your function for a linear equation, unfortunately won't work. So if you have missing values, you essentially are trying to calculate two matrices, two vectors or matrices of different sizes. So unfortunately, your equation will actually throw an error. And it'll actually tell you, it's like, I can't run this equation because there's two arrays of different lengths, or there are null values in your arrays. So a big reason of why we kind of harp on, hey, if you have missing values in your data set, you need to do something with them. You either need to remove them consistently across all of your rows so that they're the same size, or you need to fill in those values and make a choice about what to do with matrix with your missing values. Because a key component of calculating or working with different matrices is that the values need to be of the same norm or the same length. So let's dive into this first equation. So what we're going to do is we're going to manually create our X and Y matrices using the Longbones data set to solve for the slope and the intercept values. So this is a little bit, this can be kind of a lot of code to build in. So I'm just going to create a code thread on Slack now. And I'll make sure that if you are following along, you can essentially see what's happening with your array itself. So first and foremost, we want to determine what our X array is going to be. So we determined earlier that we are using nitrogen as part of our independent feature. So in order to make this work, there's a few different components that unfortunately we may need to do. And a quick heads up, there are also, I'm going to just show you a very step-by-step process just so that you can see the transformation of these values and understand the different data types that we're working with. But I want to also mention there are far easier ways to do this without this multi-step process. But if you see this Longbones nitro, this is a series value. A series value, remember, has an index. So these index values on the left and your values, which means that this isn't necessarily this can be referred to as a column, or if you were to take the shape of a value, it'll tell you that this is a one-dimensional value where it's only essentially a straight value. However, as far as certain calculations, it's important to note that pandas doesn't necessarily treat some of these data types as one-dimensional values. Sometimes you'll have to use NumPy arrays to calculate these values.
What?
Go.
I know, I'm waiting. 水果吃了都我教你
Okay, so when you convert your values into an array, you've essentially removed that index value that would be typical from a pandas series. Now note, another thing to do, or another thing to actually understand that you may need to do, is that you may need to reshape an array value in order to build it into the structure that you would need to use as one portion of your matrix, one part of your matrix. So note, you have an array, you have your series, in this case. We converted this into an array, and then we reshaped the array into a structured format that is vertical in nature. Questions so far as to this first step? So that's going to be my variable for nitro. My next variable is going to be my target value. So my target value, I'm simply going to create an array ahead of time for my time value. And that time value, I'll have to do exactly the same thing in order to treat those values. Get some syntax corrections down there into the amount of time that that body's been buried. This second array ends up being my Y matrix. Finally, remember that as part of our original matrix, we actually need to have something for our intercept to calculate from the value itself. So we need to introduce a bunch of ones into our matrix for our X matrix. So the ones can simply be created using the function, the NumPy function for ones, which is a function that will return essentially an array or a structure of ones for as many values as you want. So if you take your ones, say I want 10 ones, I can create that. Whoops. I can create an array of just a bunch of ones. And frankly, this can be as easy as saying like, oh, hey, I know I have 35 rows in my data set, so I can just say like, I just need 35 ones as an array shape. Let's make this a little bit more complex and make sure that we fit to the size of how many how many rows there exists in long mode nitros. You'll see that this is essentially still 35 values. If you need to confirm that, the len of ones, 35. Now, these ones will also need to be structured in a vertical format. So you reshape the value as where am I? That's wrong. That's not supposed to be there. There we go. Okay. Ones, where's the error? That goes there. Cool. All right. By the way, if you were trying to follow where I found that syntax, note that in Google Colab, it actually tells you where the parentheses might be missing. So if you add a parentheses, you can see where the parentheses might be. If I happen to add an extra one and it doesn't shade out, it means like it's missing somewhere. So learn to read by troubleshooting. It's really helpful. So there are our ones. Now that we have our ones, both our nitro and our ones, we can actually create our X matrix. I'm going to create our X matrix using the NumPy because I'm working with NumPy data types, the NumPy concatenate feature, which takes my ones and my nitro values, going to specify that I want these values aligned up vertically. And we now have our matrix values of ones and nitro values. Any questions so far? Okay. The next step, and I'm just simply going to take my equation just so that I can follow along, is we have our X and our Y. This means we actually have everything we really need. Whoops. That did not copy over properly. Copy. Paste. There we go. That means we can actually start building these values for the equation itself. So I'm simply going to take I'm going to create a number of values. My X prime, my X dot matrix X prime, the dot product of my X prime to X, my inverse of my dot product result of X prime to X. And to all this, we're going to get the dot product of my inverse to X prime to the dot product of X prime to X, to the dot product of X prime, to the dot product of Y. That is not something I've actually spoken aloud before, and that is really a lot to say. So let's break this down into creating the X prime value. There we go. The function to create an X prime is actually fairly straightforward because it's simply a transpose value. When you transpose your value, you take your values, you break them up into two separate arrays, your ones and your array, and your two separate lists within the array itself, and your values have been transformed into the column. The columns have been transformed into the rows itself, and that's your first value. So I'm going to identify this as X underscore T. This would be my transposed value. For my matrix multiplication of X prime to X, I'm going to say X prime to X, we're going to simply take I'm going to use the matrix multiplication function within NumPy, which returns the values of your of two different matrices. So in this case, I take my X transposed to my X. I take those two values and note that it returns this 4-part matrix that calculates the matrix multiplication of X transposed to X. This can be identified as XTX, and you return your X matrix multiplication. Quick note, XT to dot X does the exact same thing. So either method works fairly well. So we've got that first part. Let's then calculate the inverse of the value. We'll go ahead and copy this, send it over your way. The next portion, inside, like within NumPy, you'll find a tool called linear algebra. And within linear algebra, you'll find a value called the inversion function. The documentation isn't popping up as well as it used to, so that's a little bit odd. But for the inversion of the value, I'm going to take my XTX, or the result of my dot product of X transposed to X. So that's the result of this into XTX gets returned as the linear algebra, and it returns an inverse of our array results. And this can be considered our XTX inverted value. I'll share that with you as well. This array is then the first part of my equation. The second part is my x to y value, which is actually going to be pretty straightforward because my x to y value is simply the dot product of my xt, or my transposed value, to the y value that I created earlier, or my target value. And you'll see that the value, because again, we're simply working with a matrix that only has one column, will return our two values. And once you have your x to y values, you've actually got, do we have most of the equation? We have the entire equation from the inverse to the x to y. I've created the first part. Let me go ahead and identify that on the notebook. First part of the equation. Then the second part of the equation. Finally, my results would be simply my x tx inverse to the dot product of x, y. These numbers should look fairly familiar. I'll quickly take my notes from the last class where we build our model and the params. And you'll see the exact same results. Any questions?
Just all of that for what OLS does, essentially.
Yes, this is, I mean, that's the point of this class. And that's, again, that's what the classes are going to look like, or what the classes should look like moving forward. We spend a lot of time talking about, like, look, the mathematics behind a KNN, or the mathematics you would use to understand why you would use a logistic regression versus a linear regression. It's important to know the math behind the scenes, because understanding this mathematical process will, okay, in the short term, as you're learning how to code, as you're trying to get a job, as you're trying to, like, hey, I just need my code to work, you're going to find yourself deprioritizing the general mathematics behind these individual models. But the faster that you get more comfortable, like, studying or understanding the acute mathematics of any specific process, the easier it'll be for you to determine, oh, this is this type of data, or this is this type of problem that we're dealing with at work. Well, the mathematical component that makes the most sense to use would be this type of equation. Now, generally, like, that's not something like that kind of process only happens with a specific, like, there's a specific deep dive that you'll be doing over the next few months as you kind of interpret the different codes and the different models. But understanding why the math works helps you determine, I need this type of model for this type of process.
That makes sense.
Yeah,
for sure.
Yeah, no, I know it's confusing, but the like, there is an aha moment where once you see that you can quantify most of the, like, really the problem, really the interesting part starts to happen when you realize that you can quantify most of the, and we'll see an example of that in the second half of this notebook, where if you can quantify the problem that you're working with, whether it's on a sales basis, whether it's trying to determine which table is the best table in the restaurant, or which employee produces the best in sales, or whatever you want, whatever type of problem that you're trying to solve, if you can think of it, or if you can convert that into a mathematical process, you've got a, like, you can choose which model you want to use to build for this problem. Let's take a break with that in mind. When we come back, we'll take a look at how to do this with multiple linear regression. Let's come back at 15 after the hour. And we'll take a look at this one more time, and then we'll talk a little bit about cosine similarity. Any questions that might have come up behind the break, while we were on break? No? Okay. So if we're working with more than one variable, now we're essentially building the same equation we did earlier with both nitrogen and quicklime. So that means that we're going to be adding to our X matrix the value for 1. That part's actually fairly straightforward. And you can eventually even build this into a function if you so wanted to. You can take your values for X. And the biggest difference is that we're going to take the same process that we did here so far and introduce our values for lime. I'm going to add my value for long bones nitrogen for lime. I'm also going to reshape these values. It's -1 to 1. And when I concatenate these values, I introduce my ones, my nitro, and my lime values, and there's my 1 or 0. And note that this is exactly the same step-by-step process that we did above. So next, I'm simply just going to take every single step that I took here above, because my values for X and Y are going to be exactly the same. I'm going to copy paste this one step at a time. Pardon the repetitive of this. Went too far. My apologies. It's going to be a little bit of scrolling here. Here's the second part of the equation. My last part of the equation. And you return an array that calculates everything else so far. Or alternatively, yeah, you can use your model for stats models where you include nitrogen and your categorical value for quicklime returns the exact same thing. Pretty straightforward, right? So with that understanding in mind, or like we ended before the break, one of the things we addressed is how the values that you're working with are essentially taking a series of feature components or a series of everyday values and beginning to interpret how we can evaluate them mathematically. So since we're beginning to understand how vectors and matrices work, there's another component of how we can think about vectors to come up with a set of relationships between different series of quantitative variables. And so we use the linear regression to measure those relationships. We can actually measure different sets of types of values, like for example, strings, and come up with a quantifiable relationship between different sets of values. So if we think about how we've just worked with matrices to calculate a linear regression, we can also use the structures of our Python objects and treat them as vectors. And with those vectors, we can actually mathematically determine relationships between different values or different variables. So if we take a look at our vector, or at the vector we saw earlier, and we treat this as an object in space that has a direction and a norm or length, we can essentially begin to think about these values mathematically. In our case, we're going to be working with two-dimensional sets of values. Now, if we had two different vectors, or two different lines existing in space, we can essentially begin to think of these two lines in space, not just from a computer science perspective, but from a mathematics perspective. Because if you remember from your algebra or linear algebra days, it is you are able to actually measure two different lines, or for example, two different parts of a triangle. So if we wanted to measure how similar two vectors are, and if we remember that a vector in Python language could be very similar to a NumPy array or a NumPy series of values, we could essentially begin to determine, is it possible that two vectors could be the same, and so therefore could two NumPy arrays be the same? And if they're not the same, how could we measure how similar they are? So in the event of two vectors that are exactly the same, those vectors would have to be in the same space with the same origin as well as the same magnitude or the same length. In other words, if I were to change the second value in the second vector, you would see that the value essentially goes up a little bit further. So it's not quite the same. I take it down a little bit, you see that it drops down. But these are two objects existing in the same area. So we can think of it in terms of vectors and their relationship to each other. So if we look at two vectors that are in perpendicular direction to each other, in other words, these are orthogonal to each other. So we have a value where we can expect there to be a right angle in this specific triangle. We can also expect these to be orthogonal or running in perpendicular direction. So two vectors that are going in opposite directions could be considered to be opposite to each other. And that's because in this case, we have a vector that goes in one direction and a vector that goes in a completely different direction. So the way that you can measure how similar a vector is to another vector is that we can take a look at the size of the degrees in the angle between those two vectors. If vectors end up being exactly the same, there wouldn't actually be an angle between those two values. In other words, there would be 0 degrees between those angles. But whether a vector is orthogonal or perpendicular, we can expect there to be a 90-degree angle between the two vectors. So how do you determine the degree between two vectors? Not necessarily going to go into this, but this is one of those things where you, well, like, I'm not going to go into the mathematics behind cosine between the cosines themselves, but you can measure the number of degrees between two angles by essentially using the classic Pythagorean theorem to measure the square of, or the sum of the square of two values to determine the length of where that third line might occur. And with basic trigonometry, you can measure the degree of each one of those angles by measuring the cosine, the tangent, by the length of the adjacent or the hypotenuse of different triangles. So if we think about our vectors as that adjacent side of a triangle, or one as the hypotenuse, we can actually measure the cosine of the angle, measuring the relationship of the hypotenuse and the adjacent side. In other words, we can use the cosine of an angle to determine the relationship between two different vectors. So when you're working with two different vectors and they're exactly the same, the cosine of 0 or the cosine of your value being 0 will be equal to 0, and otherwise you're going to expect there to be a value of 1. So when your degree, or when your vectors are perpendicular, you can expect your cosine to be equal to 0. So when we're working with cosine similarity, a big component of how we're scaling these values is on a measure of 0 to 1. Now, because it's not just simply a vector that has two dimensions, so it's not 0 to 1, it's not essentially going to be a line. We're actually at times working with many different rows in our data. We can expect there to, we're going to expect ourselves to need a very specific formula to work with this, to determine the cosine of that angle. And when you're working with non-zero vectors, you can essentially use the dot product formula that we've seen used before, where you use the dot product of your A and B matrix is going to be equal to the magnitude of A and B to the dot product of your cosine of your cosine value. So this can, to solve for your cosine value, you've got the dot product of A and B times your length or the norm of your A and B vectors in this scenario. So let's take a look at how to apply this in a real world scenario. Let me just quickly take a look at my notes here. There we go. Okay. All right. Okay, here we are. So if we take a look at if we think about two different artists, we've got John Lennon, we've got Paul McCartney, two of the Beatles. They were both writers as part of their band, and they had essentially different partnerships where some of them, like, we all know that there are some songs that were written by each one of the Beatles. Sometimes they worked together, sometimes they collaborated, and sometimes they essentially wrote the songs and it was chosen to be part of their overview of songs. So we are, in terms of what we know about what the Beatles and what we know about interviews, they worked really, John Lennon and Paul McCartney essentially worked really well together until they didn't. Essentially, they had their own fallout. So they would at times argue whether there was a true collaboration between a song, whether one of them specifically wrote a song, or whether they admitted to having collaborated, or whether one of the other artists wrote the songs itself, like you would when you've been working together in that kind of environment. So the question ends up being, we know whether a song was a collaboration, whether a song was written by John Lennon, or whether a song was written by Paul McCartney. However, we have a couple of songs that are up for dispute. So in this case, we're taking the song In My Life and trying to determine, because we know which of the songs were collaborations, which ones of the songs were non-disputed or written simply by one of those individuals, in this case, Strawberry Fields being written by John Lennon versus Paul McCartney written by Penny Lane. This is not disputed. So we can take the text of one of the songs that was written by John Lennon and copy the lyrics of the entire song. We'll remove punctuation and make them all lowercase and determine whether the song that is disputed, In My Life, this is the disputed song, to see which one of them might have actually read it or might have actually written it. Let's start off by taking the values of the song and breaking this down into a data frame. So we're going to pre-process this entire data into a way that we can measure the cosine similarity between the different songs. So you're going to take the data frame from Strawberry Fields, and we're going to create a data frame from it. So you take Strawberry DF, and we're going to create a data frame with those songs. The data frame is going to have a column named words, which is going to be a string of words. And we're going to take the lyrics of this string object, strawberry underscore, and we're going to split the values. Just in case you want to remember what dot split does to your values itself, we're going to split it on the bottom, and note that what this does is it takes every single object in the string and splits it into something that looks kind of like a vector. when you create that into a data frame, you see you have returned a value with one column and rows and every single term. So once we have this object created, let's determine and measure the cosine similarity between these two songs by comparing how similar are, how frequently do the words show up in each song. So let's count how many times does a word show up in each song and determine how often that appears in Strawberry Fields. I'm going to use there's a few different ways that you can do this. I'm going to use the crosstab method to index the values based off of the words column. So if I have my strawberry, if I have my strawberry data frame and the words value, I am going to crosstab those values and count how often they appear. There it is. There's that. And you're supposed to go there. Cool. So what I've done is I've taken all of the words, assigned them a numerical amount. And you can do this using value counts too if you want. But I'm going to call this my strawberry frequency. This strawberry frequency, let me actually just share this with you as I go. This is going to be huge on the cell itself. And I'll take my crosstab as well. So we have Strawberry Fields as a data frame. Let's do the same with Penny Lane. And I'm simply going to copy paste this process over so that we're not too repetitive, because this is exactly the same process. So if I take my look at the lane frequency, we have our values, same thing. Copy that over, share that with you on Slack to follow along. Let's put these two data sets together. It's not actually something you have to do, but I do actually want to keep ourselves organized and fill in some of the missing values. So if we take a look at the missing values, we're going to join these two objects as a data set. So if I take my data frames, the ones that I'm currently working with, note that I'm working with Strawberry Field. Yeah, Strawberry DF. Pop-up thing. Thank you. So if I take my Strawberry DF and my, what did I name my other data set? Lane frequency. This should be Strawberry frequency. What did I call it? There it is, Strawberry frequency. That's where that was about to take that wrong. Strawberry frequency and lane frequency. So I have my two data frames. I'm going to join together those two frequency into a data set that I'm going to call all words. And all words will be concatenate. Note that because I'm working with pandas objects, I'm concatenating these two values as my DFs under the column axis. So what does this look like? For all my words, where the word fields pops up in each song, the word I, the word I'm, strawberry, A's, how many times they pop up in the song, and a bunch of nulls, because there are indeed portions of words that appears in one song versus songs that don't appear in the other. So let's take these values, fill this up with, because we know that our null values actually refer to no values present in the song itself, or that the word is not present in the song itself. I'm going to fill those null values. And then I'm going to rename my columns. So Strawberry Fields is the first column. We're going to call that Strawberry. And my second column, I'm going to call it Penny Lane. So note I've done a series of transformations to my data set. Now I have a data set that essentially shows how frequently a word pops up versus how frequently it does not pop up. So now we have enough tools to actually compare the values of Strawberry Fields and Penny Lane to each other. We're going to use the NumPy values for the dot multiplet and for matrix multiplication, or the same dot value that we used earlier. And we're going to use from our linear algebra package, the norm function, which will count how many times a norm value appears or essentially measures the length of the data set itself, or the length of the vector, excuse me. Note that all I'm doing is I'm essentially applying the same equation to both columns. I'm going to treat each column as one of the vectors for this object and calculate it. So in order to do that, I'm going to use the dot function, which requires me to include, it is a pity that the dot, like, why is this not popping up? So the documentation for this requires me to use the matrix multiplication. Let me just take the equation and bring it down. Take that down here and measure that out. So the dot product of A and B, my first column, is going to be all words, strawberry, because that's the first column name. And the dot product of those values to all words and Penny Lane. What did I call it? Did I call it? Yes, I called it Penny Lane. So note, this is a dot product that will return a dot product value for those two sets of values. That is my top side value. Note we are dividing then by the norm of these two sizes. So that's going to be my numerator, and my denominator will be the norm of all words and Strawberry Fields times the norm of all words Penny Lane. So when we've compared the Strawberry Fields to Penny Lane, what we return is a cosine similarity of 21. Ooh, okay, I kind of skipped some stuff, or I didn't skip anything, but I just got ahead myself as far as the instruction. So I'll take this comment out, bring that in here for us. Here we go. So this song, or the song Penny Lane, is a Paul McCartney song, and Strawberry Fields is a John Lennon song. So we have two songs that were independently written by each one. Strawberry Fields written by John Lennon and Penny Lane written by Paul McCartney. So our baseline can serve as, hey, the similarity when they're working independently ends up being 0.21. So then the question ends up being, is the songs when they're collaborating, is there any, like, is the value greater than when they were working independently? So let's take in two more songs. We're going to go through the same process where we take the songs From Me to You, which is a collaboration, and In My Life. This is a song where we're arguing, who actually wrote the song together. So we're going to take the same process From Me to You. I'm going to do some copy pasting here so that we're essentially repeating the same process. This is our disputed song. We've got Penny Lane to In My Life. And if we wanted to measure the songs In My Life to Penny Lane, we can then compare all of these different sets of values. So between Penny Lane and In My Life, again, Penny Lane is the Paul McCartney songs, and In My Life is the disputed song. So Paul McCartney to the disputed song has a cosine similarity of 0.35. If you take the next song, Strawberry Fields, to In My Life, so the John Lennon song, notice that the value is a little bit lower. So John Lennon to In My Life, not as close or not as high as the Penny Lane song. And finally, if we were to compare the songs In My Life to From Me to You, essentially the same process, the collaboration to the disputed song, we see that we get a cosine similarity of 0.333. Based off of doing this search, the songs Penny Lane to In My Life has the highest cosine similarity between all of the different comparisons that we've just done, at a number of 0.35, which is a little bit higher than the baseline value in terms of angle. And it is highest when compared to the songs where they actually collaborated together. So the cosine similarity to In My Life to all other songs is higher than the cosine similarity between Strawberry Fields and Penny Lane, like we just said. And the relationship between In My Life and Penny Lane is technically the highest. Now, if you look into additional research, if we talk a little bit about these collaborations, you can talk a little bit about how they disputed which songs they worked with. But if you take this process and consider this cosine similarity, we can potentially say that this analysis using cosine similarity might provide some additional evidence that Paul McCartney really did write the song, or more than an additional portion of the songs In My Life. Let me go ahead and open this up to questions, because I suspect you might have some.
Just curious though, would this be like kind of the same process you would be doing if you were doing this on like the musical side of it? Like if you ever, however you made the music into a data frame or whatever, but it'd be that same process essentially, like going through that with set of lyrics.
There are a couple of different models that you can use. This is just one mathematical model that you can use to measure like if you're trying to measure how often, so for example, if you were to take a song and break it down into how many beats are in, I'm not super familiar with, I'm going to butcher the musical lingo behind this, but if you were to take how often is a specific beat used, or how often is a specific tone or something used in a song, and wanted to compare it based off of frequency, you could use something like this. But you can also use other types of models. This is just one model that you could potentially perform using after having converted your values into, after having converted your words into the frequency of words, and then converted that frequency of words into essentially what we're doing is a calculation on the frequency that a word appears on. But if you wanted to measure based on the frequency of beats, you could possibly use cosine similarity to measure a similarity between two songs. So the answer is yes, you could potentially run a test like this, as long as you're specifically determining what it is that you're quantifying as part of your test. Does anyone sense something wrong with this process, or is there anything? Let me see if I can bring us back to this part of the data set. What are some of the limitations that you see?
They're not having a lot of the same similarities or similar words.
Mhm. As you work with different natural language processing techniques, again, this is more of a Unit 4 concept, it's important to notice that a couple of these words are fairly common. And whether you can measure the specific values of a, like whether, like the reasoning we're taking is that we are basing this comparison on the frequency of how much a word is used. Now, in this case, you could technically say that, well, there is some amount where how often does a specific writer use the words a as part of their song, or how often does a specific term gets used. There is a specific argument you could make for, well, you can't really include a proper noun as part of your song in this comparison, because obviously Penny Lane and Strawberry Fields are not going to be present in one song versus the other. So you would have to do a lot more cleaning to the data set beyond just lowercasing and splitting the values. So there's a specific set where we've looked at the model, looked at the conclusions, and realized, I think this model requires some additional cleaning. So this is where you would have to go back to the data set itself and do some additional restructuring just to make sure that you're working with exactly the same set of values, so that this comparison might potentially work. Other concerns or other limitations that you see off the, like from the top of your head?
I mean, I just was curious how we supposed to know if Lennon or McCartney actually wrote that specific word that we're now quantifying or whatever inside of the lyrics itself. Like, how are we supposed to know that difference? If it actually was McCartney or Lennon, we know it by them being the non-disputed writer of the word, but I just don't see how the comparison, I guess, is being made. But
right. So the only way that we can determine that is by having a sufficient enough baseline. So one of the things that's important to note is our baseline accurate enough as a baseline? Is this type of song significant? Like, is this song, like we started off with the baseline of Strawberry Fields and Penny Lane as our baseline song. So is it possible that we can expect there to be a very similar cosine similarity between two different sets of songs? And with that different baseline, how significant could these similarities be for these additional values? So as you can see, even when we're working with two songs that were the songs that they all wrote individually to compare to the disputed song, do we determine that those songs are representative enough of their actual oeuvre? It is important to be able to recognize that you're going to want to, like, for a process like this, it's pretty helpful to run multiple baselines and compare those baselines against each other. So up until this point, note that the conclusion we came from this particular test wasn't necessarily a definitive conclusion, but a conclusion of, I think we need to do an additional exploration on this. A lot of times when it comes to the kind of work we're doing, it's very important to determine all that we're doing is coming up with a mathematical reasoning for our conclusions, but there's never necessarily a definitive answer. It can serve as potentially additional evidence that Paul McCartney was, or the similarity between one set of lyrics and the other seems to track. But to define it as, hey, this is the answer, or this is definitively what happens, is a little bit risky. Let me add one quick thing here because we've gone through this whole process. We took our strings, converted them to data frames, filled the values, renamed the column data frames, join these two values together. There is, of course, an easier way to do this. And I'm always going to make sure that we specify that there's an easier way to do this. So in SciPy, there is a tool called Spatial. Spatial is a library that includes a lot of the mathematical components that you use to measure distances between vectors, between distances, between different values in a 2, 3, or multi-dimensional space. Some of the tools that you can use within Spatial include, see if we get the thing to pop up. I'm getting a lot more tools than I just, this is odd at Google Colab. I'm not a huge fan of this. All right, let me just look up SciPy Spatial. I just want to look up the documentation. SciPy Spatial, the docs. There it is. There's the .orgs for this. Yes. So the spatial transformations have a bunch of different types of tools that you can use for your different functions. You'll be seeing the Minkowski and some of these other geometric measures. Within this particular tool, I want to call the distance values. Distance values, there you are. And within distance, this is not, I don't like that the thing isn't popping up for me as it used to. So if you look at the distance documentations, you'll see that you have a bunch of different tools that you can use based off of those different objects. I don't expect you to know all of these, but I do want you to see that you actually have a way to measure or compute the cosine distance between one dimensional arrays. So if you take the cosine values, yeah, it's odd that the documentation isn't popping up correctly. And we understand that we need a set of arrays. We've actually ended up building those arrays as part of a pandas columns. So if I've got my first value, all words, and I want to use, what am I doing above? In my life. And my next array is all words from me to you. That's this equation up above. Hang on. One quick thing to note is that you will measure the values or the distance between those arrays. But because what we're trying to measure is the similarity of those two values, you're subtracting the value of that distance by 1. And note this returns the exact or close to exact same thing. So just an easier tool if you're if you go into more cosine similarity computation. All right, folks, any questions? All right. So with that said, if you have any questions, bring them up. Justin, stick around for just a second. I want to take a look over like behind the scenes on your side. Otherwise, I will see you tomorrow as we go into evaluation metrics that you would use for calculating your linear regression models performance. We'll have our last class tomorrow, as well as the beginning of your last sprint challenge for Unit 1. But if you have any questions in the meantime, feel free to reach out. I am on Slack, so check any messages you may be keeping up. I'll be doing a little bit of an audit of the grades as far as your individual values for your sprint assessment and sprint challenges, just to make sure that you are on track to succeed and move on to Unit 2 over the next few days. But otherwise, look forward to chatting with you tomorrow. Have a great day. Okay, I'm going to go ahead and pause the recording.